Okay, so I'm going to cover this question, which is typically asked in companies, which is called design a visual search system. And chances are, if you're interviewing for Amazon's visual shopping team, or maybe for Pinterest, or for any of the e-commerce companies, they will ask you to build this kind of system. So, what the idea is that generally you are as a user, you go ahead and capture a picture, and then you select like a certain region in the picture, and then what you have to do is basically build a search engine which takes this picture as input, and it outputs like a list of products which are similar to this photo in the picture. And then the user can actually go ahead and look at these individual pictures and click on them, and then he can actually add them to the cart and then maybe buy it. So the point is that why such sort of systems are important is because traditionally, like before computer vision was a thing, you used to just enter what you want by typing it in the text box. But here, like what is important is that basically you are able to capture the image, and then you can use like some sort of computer vision system to find what you are actually looking for. And if you are able to do that, and that's why the author these people who wrote the book, they are calling it as a visual search system. So here is a typical conversation which will go ahead in case of like, so if you are like interviewing, and like let's say you are a candidate, and there is a other person on the other side who is trying to who posed the question for you. So this is like a sequence of things which you could ask him. So the key point is that he will ask you to build like a visual search system in this way which I told you, and then the conversation will go as follows. So first, like you should ask him that like in what order the system should output the ranking. So basically like we should first output like the most similar item. We should first output like the most similar item, and then we should output like the most similar item first, and gradually the least similar item. So that's the point. And then the interviewer will generally reply by saying that, okay, you should output like the items. So for this chair, like you should output the item which is most similar first. So like this chair is like most similar, so they should come on top of the in top of the UI, and that is what you care about. So this is like rank 1, rank 2, rank 3, rank 4, and so on. And so the other question is that whether you should focus on images or videos, and the interviewer will generally say to you is that let's focus only on images, which is a pretty good thing. And then okay, then the other question is that should we actually display images which are personalized for a user? So like for example, if I were to use a visual search system, if I were to go to Amazon and search for something by a photo, and you were to go there, should it always output like a different output or a same kind of output for both of us? So then we are assuming here that we are not focusing on personalization. So if multiple users are using this type of system, the system will always output like a similar ranking. So it is not customized according to users. Now this might seem like a flaw, but an interviewer will be interested in knowing, like we don't want to like customize it for a user, but we want to make something predictable. Okay, now the other thing which you can ask the interviewer is that can we use like the metadata of query images, which in our case is like, for example, when you are capturing an image, it might contain like image tags or things like that. But so you can ask the user the interviewer that can I use like some sort of metadata to build such kind of system. And the interviewer will generally reply that the interviewer will reply that okay, you can take a model which uses like the image metadata, but generally like we are concerned with building a vision system here which only operates on the image pixels, which is like pretty important. And then the other thing is that now we are like concerned with users interaction with such a system. So for example, you gave it a photo of chair and then it recommended some chairs. So are you allowed to maybe save chair or like it? And these actions are like important for us. So uh, the interviewer will like say that okay, for a simplicity, let's imagine that you are only allowed to click you're only allowed to like click the given image, and there is nothing more. And then the candidate says that okay, are we allowed to like moderate the image, like whatever we are outputting, it should be an actual product, and it should not be like some sort of offended product, like yeah. So the key point is that the interviewer will say that, okay, we want to keep like it safe, but like content moderation is out of the scope. Okay. And then so if you notice here, what the interviewer allowed us to do is basically he told that we can use, so while a user is interacting with the system in such a way, basically he can click on the image, right? And what you can do is like you can use like the user interactions with the image. So for example, you went and you gave it a chair, it gave you like certain recommendations for a chair, and let's say you clicked on a chair because that was a product you really liked. So the user click here is actually like a positive feedback which you can use to train your data, which means that, okay, whatever image you clicked and whatever images you did not click, the one you clicked is actually having a higher ranking which you prefer rather than the other thing. And let's say that you have data from millions of such users, what they clicked, so you know what is like a positive data, and what they didn't click is what they actually skipped, so that is negative data, and that is something which you can really use. Okay, now the other part is that so we have taken care of like the user's interaction with the system, but we also need to take care about like what is the latency which we want in our system. So for example, let's say that Amazon has a database of 100 to 200 billion images, and you gave it like a photo of a chair, and now it wants to compare this photo against 100 or 200 billion photos. Obviously this step will take like certain a large amount of time because there are several photos, so your system should have the ability to retrieve like the images pretty quickly, right? So now that is an assumption, and we need to make it clear for the interviewer to know whether this kind of assumption is something which we should optimize for. And turns out that the interviewer will say yes. So once like you have done this type of back and forth with the interviewer, generally what you should do is you should summarize the problem statement which you are trying to solve here. And the problem statement is basically we want to design a visual search system, and then you can give like a query image to this system, and it returns like a list of rankings based on similarity to the queried image. Okay, and for simplicity, you are only typing like you are only using images, and video and text are not required. So you are building a system which is purely computer vision system. And for simplicity, like right now you're not concerned with user personalization. So two people are using the same if two people are giving the same query, the output of the system will be the same. Okay, so once you have finalized this problem statement, what you generally have to do is that you have to frame like your problem as a ML task, and that is a task which the interviewer should agree for. So in this case, what we want to do is we want to retrieve like we want to build a system in which like you can take a query image as input, and then outcomes like, so you send like this dog, and outcomes like a variety of dogs. Okay, and so this is like the highest rank, so let maybe rank 1, rank 2, rank 3, rank 4. So this is a dog, and you want to build a vision system of this. Okay, so you have a visual system which takes as an input query, which takes like as a query input, and then you have a database containing like a lot of images, maybe a stock of inventory of whatever, a stock of like all the product images which are available in the Amazon, and you want to retrieve like the top 5 dogs or whatever cute dogs are here. You want to retrieve something that like that. Okay, so in case of like ML, so the key point is that you formalize this problem by saying that you are trying to build a model in which you take as input a input image, and you want to output like a set of images, and you want to output them in a ranked order. So in this case, like you are outputting these 4 images, you should also know that this is like rank 1, rank 2, rank 3, rank 4, because once you have these 4 images, you can easily display the thing which is on the top on the in any way you want to build a UI, right? And that's like a job of a UI person. So this is the point. And how do you, so this is like a ranking problem where given an input you have a multiple outputs and you have to compute like a ranked list. So how do we go about this? And what you can do is you can take this idea called representational learning, and what representational learning actually does is that, let's say you have a system and you're trying to feed it an image, and generally what you will have is you will have like a image which is like pretty high, maybe 512 by 512 by 3 dimensions, and this is generally like a RGB image, right? So each of the input pixels in this takes the value 0 to 255, and this is like a pretty large image. So if you compute like the number of pixels, number of the size of its array, it's 512 by 512 by 3, and generally like you will pass it through a model, and what your aim is that your model will spit out like a higher dimensional number. So maybe it compresses all of this image into a higher dimensional number which is like 1024 dimensional. Okay. So so you have an image, but a network can't understand what is in the image pixels. So you build like a model, a computer vision model, which is trying to understand what's happening in the image, and then you are actually predicting like a higher dimensional representation of it, which in our case is 1024 dimensional, and this representation is generally known as embedding. So the key point to understand is that computers can't understand images. So therefore, like a lot of research has gone into how to represent, like, let's say, words into numbers, how to represent images as high dimensional numbers, and like whatever is happening. And these type of embeddings are also known as vectors. And this is the whole job of a machine learning algorithm, that how do you build something which is like really high dimensional representation of your image. So in this case, one point you have to realize is that your image, which was 512 by 512 by 3, is actually compressed to 1024 dimensions. Now it is compressed because like 1024 is obviously less than this number, but you can imagine that 1024 is still like a very large number, and it is important to keep that in mind. Okay, so now the next point is like how will the processing look like? So let's say that you have two images, image 1 and image 2. Let's say you have two dogs and you build a ML model, and what it will do is that it will crunch out like these different vectors. So it will give you a vector 1 for image 1 and a vector 2 for image 2, and in both of these cases it can be 1024 dimensional long. And what you will end up with is that, okay, you have these two dimensional these vectors, and you have like this embedding space. So let's say that these two vectors, these two images are close to each other. So you want to like somehow use, so when you have like a bunch of images, you can find like these sort of points in the embedding space which contain like different type of images, and each of these points corresponds to like a given image, right? So now let's say that you are given like, so let's say that you want to predict an image which corresponds to this dog. So what will happen is that you have a dot which corresponds to this dog. Okay, now what you're concerned with is actually retrieving like some sort of, what you're concerned with is actually retrieving some images which are very close to this yellow region. So in this case, maybe you want to retrieve this kind of stuff, these embeddings. So like you have to like retrieve like maybe 4 or 5 of these things which are closest to it, and this is how you can actually do this job. Okay, so you can so for example, here is an example which is showing that. So let's say you have a query image of a dog, and then you embed it, and you are searching for like 3 similar images to that, and assuming that you can learn a function which can transform any image into like this sort of embedding space, then it will be like there will be 3 dogs which are very close to this, and you can actually compute like the distance between them, and you take like these 3 closest crosses, and that gives you the notion of similar images. Now obviously, like if you want to build something which can take an image and embed it into this higher dimensional space, it can have like any implementation, and that can be any ML algorithm. We are not concerned with that because it's not our job to build the model, it's our job to build the system. So that's one mindset which is really important for you as a PhD student, because we have spent a lot of time building algorithms, but we don't know how will it play in the bigger role. Okay, so this is the problem definition, the ML problem you are trying to solve. Given an image, given a lot of images, project them to a higher dimensional space, and then for a particular given point of the query image in this space, you are trying to find like the k nearest closest point to it. So now the key point is that, let's say you want to train this system, how will you prepare the data for this? So the key thing like which in which the way, so what are like the good features which you can design for your system. So the key point is that when you're trying to think about this, try to think about like what are the sort of moving parts in your system. So here, like the key point is that we are building a visual search system, and in visual search system, like we have a user, we have like some images of the inventory items, and then you have users and images interaction. And remember, that is something which the interviewer permitted us to use. So now you can imagine, now you should start listing like the features for each of these categories, like what sort of features come and how you could use them. So for example, let's say we only take a look at, let's say we are only taking a look at the images. Okay, so in an image, when you are capturing it, maybe you know like what's the name of the person who captured it. So for example, in Amazon, if you have like multiple sellers and they put like the photos of their products, then you know that okay, this seller is having that sort of image, and then you know the owner ID. And let's say that there is one seller who is like very popular on Amazon and you want to recommend that seller's products to him, then this particular feature will become pretty important. And then you have upload time. So for example, let's say a person uploaded the image very recently, that means that is a very hot product and it's like more relevant. Obviously you want to get something which is more recent as compared to something which was built like thousands years in the past. And let's say and there are like manual tags. So sometimes like the person who is uploading it might have like manual tags. So for example, zebra, pasta, food, kitchen. So he might also like label the image, and obviously this will help you know, like this will help provide you like some sort of label information. So for example, you have an image and then you know that it's tagged as a zebra, then you know that okay, there might be a zebra in this image or something like that, and that can actually help to improve the performance of your system. Okay, so these are like some of the features which are really important while you're collecting the images for your system. And then let's say you're talking about users. So what sort of users you have? So when you are talking about building a system like Pinterest or like Amazon, generally there are two types of users, right? One user is someone who is actually using the system as a customer. So that is a customer, and then there is a user who is actually selling something on Amazon or Pinterest, and that is like maybe a seller. So there are like separate features which are possible for both of these categories. And in this case, like what are some information which you already have? So let's say a person has already created a profile on Amazon. So then you can imagine that these sort of features are all which you can use, right? So you have city, country, email, and all these things. But the key point is that the user told, the interviewer told us that we want to build something which is not personalized. So in this case, like there is not much information which we can use from the customer, but there is a lot of information which you could use from a seller, because whatever information is of the seller is important for all the customers in Amazon. So it means that this particular feature is very important and this feature is not that important because we are not personalizing our interaction. Now, the other thing which you can do is you can build like some sort of user image interactions. So in user image interactions, basically, let's see what kind of things happens. So let's say there is a person who opened up Amazon in his nearby region, and then what he did is that he clicked it, and you captured like the longitude and latitude and like what was the time when he clicked on the given item. So let's say that I am in Florida and I'm searching for, let's say, what are like good umbrellas in Florida. So obviously like the system can look at, okay, what are the other people in Florida who search for umbrellas, and look at what they bought, and they can suggest those recommendations to me. So in this case, like it is really important to know like where you are present, and then the system can give you recommendations according to the geographical location. So that is like a feature which you can easily collect, because when you are in a browser, your browser shares like the location information via caches, via cache token, to the server of Amazon or Pinterest. Okay, so now this much is for features. And obviously, you once you collect all these features, you should be but in this case, like you're trying to build a visual system, a system which just takes an image as input. So what you could do further is, okay, so once we have discussed like the feature design for users and the normal images, then the next part is that how do you actually build a model. Okay, so the it is better to stick with neural networks because they are they are learnable type of models, and they can easily learn representations like which can get from images to this embedding space which we talked about earlier. And it has been shown that neural networks are learning representations versus like handcrafting representations. The learning methods are actually performing better in most of the things. So that's why like we are gonna rely on neural networks. So let's say that, so what the neural network will do is basically that it will take like a input image, and then you will have like a couple of layers which are like convolutional blocks. So and then whatever representation you get, you will output it through MLP on top, which is like a fully connected layer, and it will convert your image into this higher dimensional embedding space which we are talking about. And this whole system is gonna be trained end to end by a gradient descent. And then how, like, what will the data set look like, and the what will the data set look like, and what will the training objective look like, we will talk that about in a bit. But the key point, like the one important key point, is that sometimes people ask that what sort of neural network should we use. Should we use like a transformer, or should we use like a CNN like ResNet? So if like most of the people in interviews say that we should use transformers because transformers perform as good as CNNs, but that's generally a wrong reply. So what you can do is you can generally say that okay, transformers. The reason is that if you are given like a very less amount of data, then transformers don't really work well because they require like a lot of data. So if you are given less data, then you can use like some sort of CNN, and if you're given like more data, you can actually use some sort of transformer, and that's like a really good thing. Okay, so now that is clear, let's come on to how will we actually. So let's say that we are given very less data and we use a CNN. So the next question is that how do you actually train such a thing? So the key point is that the common technique like which you can use for training is something which is known as contrastive learning. And contrastive learning is like around 5 or 6 year old idea, and it was like originally introduced by Geoffrey Hinton and another person called Ting Chen, and I think that paper was published in NeurIPS. So what it says is that let's say that you have a given image which is of dog, and you want to like learn the representations which are good for it. So what will happen is that uh, so when you want to learn representation of dog, okay, so the way like you will train it is basically along with the dog, like you will sample like 4 images from your data set, and in these 4 images, let's say there is one dog. Okay, there is one dog, and all the other 3 images are not a dog. Okay, so this is like one of the guarantees that, so like when you're training the network, you have one query image and then you sample n images, and out of which only one is belonging as dog, and other n minus one is like dog, and other n minus one images are negatives, so they are not a dog. So the way like you train a neural network is you tell the neural network that okay, this dog should be closer to this dog, which is the dog present in the data set, and these 3 images of different kind of these 3 images of different classes should be far away from dog because they are of different classes. Okay, so now the key point is that how do you actually construct a data set like this? So for example, let's say you have a query image and you know that it's a dog, then obviously to build like such to sample like these type of n images, you need to know which other image is a dog and what are the images of other classes which are like n other classes. And so you need like a label for each of the images in this case. So you need to know that this is a snake, this is a dog, this is maybe a deer and a house, in order for this algorithm to work well. So how do you actually create a data set like this? Okay, so what this means is that basically the key point is, so this is like just what this figure is just saying, that you have like one image which is the query image which is a dog, and then you have n minus one images which are like not a dog which you sample, and there is one image which is actually a dog, which is like a positive image. And what you want is so now like what are the what are like the ways in which you can generate like these labels. So the problem is that okay, you have a lot of data. Let's say you have a 1 billion images, and you want to know whether they are, you want to know like the classes of each of them, right? So you want to know like what class each of the image belongs to. So what is the way like you can get this data? So one of the ways which you can get this data is you can rely on a human annotator. So you can go to Amazon Mechanical Turk and ask the people to label like a billion images for you. And as you can imagine, billion is a huge number, and it is really tough to get this type of data even for classification. And the example is ImageNet, which contains like a million images, and it took like, I think Andrej Karpathy took a summer off to actually label that, and he was able to do it alone. Maybe some other people were involved, but when we are talking billion scales, it's really tough to get like a data like this. Okay, now the other point is that sometimes like okay, you can create like user data. So for example, let's say you build a recommendation system, and then initially you gave it a dog, and it gave you a lot of other recommendations, and the user actually clicked at some image. So maybe that the user, whatever image he clicked at, is actually a dog, and what he didn't click at is something which is irrelevant. So maybe you could imagine that what the user clicks on is a positive data, and other images he does not click on is a negative data. But like the problem is that, so for example, let's say you have a dog, okay, and you displayed maybe 20 other images, and the user clicked on an image. Sometimes people might not click on the dog, right? They might just say some very beautiful lady, and their attention just goes to the beautiful lady. So the clicks like which you get from the users can be noisy, and it remains like a point of research. How do you actually get rid of such things? How do you actually learn from such noisy user supervision? Okay, so now there is another way which in which you can create like artificially create like a similar image. And the point is that let's say you have an image in the dog, so you know that it's a dog beforehand. So even if you don't know that it is a dog, what you can do is you can rotate this class, and you can, since both of these are essentially the same versions which are rotated with respect to each other, you know that they are like pretty similar. And similarly, there are like several images which are like houses, and these all images are like dissimilar. Okay, so now this type of approach will have two problems. Okay, as you can see, it has two problems, and let me tell you what problem it is. So let's say that you have this dog, and then you rotate this dog. Okay, and in your images you have another dog which you sampled. So the point is that in this case, like when you sampled a lot of data, and you have like one image which is like the rotation, maybe you rotated this dog by 90 degree, and you have another dog, then technically you cannot treat this other dog is a negative, because that creates like a big problem. So what the other, so that's why like you can, because you cannot guarantee that while you are sampling these other n minus 1 samples, there is no other dog if you don't know like the labels of anything. So this can introduce some noise. Now another problem is that so yeah, let me imagine about another problem. Okay, so let's say, so for example, sometimes what happens is that there is some object like which looks similar if you rotate it or you keep it. So for example, let's say that you are given a square and you are given a diamond. Okay, so now technically these two objects are different, right? Because one is a square and one is a diamond. So if you rotate like this square by 90 degrees, you get a diamond, right? So technically both of these are closer together, so the network will like try to bring like these two together closer to each other. But the problem is that one is a square and one is a diamond, and technically the network has if you try to like rotate it and then try to pull them together, then the network will say that the square and diamond are same, which obviously they are not. So the key problem is that the network, if you just try to do contrastive learning in this way, it does not actually retain the information of the angle by which you rotated the object, and that's like a very bad scenario. Okay, so now the key point is that there is some approach where you can rely on humans to do the labeling for you, and that's called a fully supervised approach. And there is an approach in which you can actually create the data by actually rotating the samples, and provided that you can guarantee that other n minus 1 samples are actual negatives, then this is a approach which does not use any data, and it is like a SSL type of approach. Okay, so now you can imagine that your data, that your network is actually trained in two phases. In first phase, you take like this fully supervised data. So sorry, in the in the first phase, so you, in this way, in when you're trying to rotate the data, actually you can do that for a large amount of images, maybe 10 billion or trillion of images. So you can actually train like your model in a unsupervised way, and this will not consume any labels, and this step is known as self-supervised learning, and you can run self-supervised learning on your model in the initial phase. And then in the second phase, what you can do is that you have like a fully supervised phase, that you, let's say you have a small amount of data, maybe ImageNet, and that has been labeled only by humans. You can actually fine tune your network to know that, okay, that fully supervised, that this is the correct label. And even though like there was some noise introduced in the learning process during the self supervision state, when you actually fully supervise it, hopefully that will go away, right? So that is like the key point, that you can imagine pre-training the networks. The first phase is self-supervised, and the second phase is normal supervised training. Okay, now the key point is like, what is the loss function which you will use to train such a network? So so you can imagine that, for example, let's say you have one query image. So let's say this is one dog, and you sample like n images, out of which there is one other dog, which is a positive sample, and there are n negative samples. So what you can imagine is that the neural network is actually making a forward pass, and it's predicting like the embeddings for each of these images. So now what you want is that the embedding of the dog should like close to each other, and the embedding of negative data should lie far away from each other. So you want like to push these embeddings together, and you want to push away these embeddings away from each other, because you're trying to like make a structure in the representational space. So this is like a intuitive diagram, but how do you actually do that in practice? So what you can do is that, let's say you are given like a positive image, which is a query image, which is the dog image, and you are given like n images. What you can do is that you can compute like a dot product. You can compute like the dot product between these two images, between all the images. And then what you want is that you want like the vector which is of EQ and EP to be similar. So if you have two vectors, and they are like pretty similar to each other, then obviously what you can do is that, okay, so if you have two vectors and you want them to be pretty similar, then if you imagine that they are similar and you take their dot product, then vector A dot B is equal to mod A mod B cos theta cos 90, which becomes 0. So you can see that the dot product is 0. So what you can do is like you can create like a loss function which is 1 minus the dot product. Okay, so let's say that your network ends up with something which is very similar. So in that case, sorry, yeah, so let's say that you have something which is very similar. So let's say that you have like 0.95, which is a very high value, that these two embeddings are close to each other, and these other values are like very low to each other. Okay, so now you can imagine that there is a label. So there is a target which tells you, okay, that the dot product, like, so whatever like the network predicts, it should be pretty high. So your value should be pretty high, 1. And then the values which are corresponding to the other classes, which it should be pretty low. Okay, so here so these all should belong to like class 0, and this is actually known as like the cross entropy loss. Okay, so now in this case, so here like there are several points which you need to understand. So the first point is that we have like there's a higher embedding space in which there are several embeddings. So let's say this is embedding 1, embedding 2, embedding 3, embedding 4. So there are several ways in which we could measure the distances between them. So for example, you try to measure the distances between these as a measure of L2 norm. Okay, so if you're trying to measure the distance in L2 norm, what will happen is that you will have like a very high value, and there is something called a curse of dimensionality which happens when you try to measure them on this metric. So the Euclidean distance is actually generally not that great, because what happens is that it faces this problem of the curse of dimensionality. And what does the curse of dimensionality mean? The curse of dimensionality basically means that when your dimensions grow, so let's say you have 1024 dimensional vector, and uh, it is like 1024 bits, okay? It has like 1024, so let's say it has 1024 dimensions, and every of these numbers can be any possible value between 1 to 10, okay? 1 to 10. So then the number of possible values which you can take is 10 to the power of 1024. And what will happen is that most of the space you have is, so this number is like pretty large. It is like more large than the number of atoms in the universe. And when you're trying to actually, so when you have even if you take all the images in the world and you try to embed that in this space which has so much volume, then what will happen is that you will end up with things which are not like really close to each other, right? So what will happen is that everything will be so far away from each other that even if like you measure the distances between them, they will not make sense, because most of the space is empty, and it becomes really hard to drive like the, so there is a lot of degree of freedom, because this is 1024 dimensional space, and the embeddings can flow anywhere, and it gets really hard to know like which embeddings should be brought closer together, and the network's job is like getting very difficult. So you can imagine this is a space with most of this is empty, then how do you navigate from one point to another? So one way I like to explain this is that, for example, you consider all the universe and you want to go to a particular star. Okay, so now the point is most of the universe is empty, and even if you fill it with a lot of stars, 90% of the universe is vacuum, right? So it is very difficult to get any kind of meaningful structure in such a high volume space. And that's the reason you use a dot product, because what the dot product does is, so if you have like two vectors, what the dot product does is it actually reduces the length, it normalizes the length of these vectors so that all of your data lies on a hypersphere. So hypersphere is an imaginary sphere. What happens is that it's a sphere which surrounds the origin, and distance of any point on this manifold is just 1. So you can compress all of your space, 1024 dimensional space, by normalizing it into this hypersphere, and then you can compare the distances. And that actually, since you constrain the volume of the space, you can actually fill it with a lot of data and still get like a meaningful structure in it. So what the curse of dimensionality is, what curse of dimensionality means is that so it is like this problem. To learn good representations, you need high dimensions. And if you go into high dimensions, the volume of data you need to get meaningful structure also increases exponentially. So you cannot build like high dimensional representations without increasing the volume of the data. And that's why like you need to train neural networks on such a large amount of data, and that's why there has been this era of deep learning. So if you somehow like found a way to retain the structure by keeping the dimensions constant, and still you manage to show that okay, you can encode like similar features in low dimensions, then technically you don't need that much amount of data. So that is like a intuitive understanding. And one other way, so you can, so that's how like you construct the loss of such a model. And what you could do is you can also leverage like a pre-trained model, because obviously you will not want to train this for your task from scratch. You will want to train like you will pick up a model which has been made by maybe something like Meta, and you will try to roll it out and try to fine tune it on your own data set, and you will take it from there. Okay, so let's say that so we described the data set, we described the model, which is a CNN, we described how you will train it, which is as a contrastive learning objective, and we discussed how you can get data, which is manual user labels, or you rely on unsupervised type of learning, where the input image is rotated. Let's say you manage to train this data, how will you actually evaluate it? So there are like two types of metrics. One is called an offline metric and one is called an online metric. So what does this mean? It means that just before production, generally you try to evaluate your model on offline metrics. And if it does a good job on that, then you know, okay, it is doing really well. And then what you do is that you actually roll it out to real world, and then you measure its performance while it is like online, while it is running on the fly. So you will have some metric which does not take that much time to compute, and that's how you will build it. Okay. So what are like some of the metrics? What are like the some of the metrics which you can use? So there is like one metric which is known as mean reciprocal rank. And what it means is, so let's say that you're given a query image of a dog, and in this case, what you want to do, and in this case, let's say your model returns like five items to you, out of which like here only the dog is present as a third item, here the dog is present at first and fourth position, and here you have two dogs present at third and fourth position. Okay, so 1 2 3 4 5. So here you have like the third dog present at the fourth position. So here you have one dog, two dogs, one dog, two dog, and then two dogs. And what you do is like you divide, so you compute like the mean reciprocal rank as 1 over what is like the position of the first dog in the list. So in this case, so here like the dog is present at position third. So here like the dog is present at position third. So what you can do is you can put a 3 here, and similarly here like the dog is present at position 1 and 3. So but the first dog which is present in this list as position 1, so it becomes 1 over 1, and here similarly it's 1 over 3. And then you can, so like for all these different kind of query images, you compute like this score and then you average it. Okay, and that's what is known as the mean reciprocal rank. The problem with this is a symmetry issue. So for example, let's say you have two model outputs. So let's say you have two models which you trained, and like for a same query image, let's say for a dog, what it does is one gives you like a dog at this location, it gives you three dogs, and one gives you only one dog. So technically you can see that this model 1 is better than model 2 because it has managed to give you three dogs, and here it has only managed to give you one dog. But since like mean reciprocal rank is only computing like 1 over like the first position of the dog, here it is essentially neglecting these two positions, and that's not good. So in both of these cases, mean reciprocal rank is computing like 1 over 2 and 1 over 2, and that is not a good thing. And that's why, because it is losing the information of all the other items in the list which are not at the first place. And that's why this is the model measures these two as equal, like the metric measures these two models as equal, but we can see that model 1 is good, and that is something which is really important. Okay, so then there is another metric which is known as the recall metric, and what it says is that among like the top so what are like the total number of relevant items and how many elements are present in the top k of the list. So for example, let's say let's say that you have like 1 million dogs, you have like 1 million dogs in your data set, and then in like maybe top 10 you only got like 4 dogs, correct? Then your metric will be this. Okay, so now the problem here is that this denominator. So let's say you have like two classes, dog and cat. Okay, and in cat, like let's say cat only has like 2 items in the data set, and dog has 1 million items in the data set. And let's say your k is 10, you're trying to retrieve like 10 items given a particular query. So in this case, if you measure like the score for dog, the recall for dog, what you will have is, let's say you predicted 4 dogs here, and here you predicted just 1 cat. So here the metric will be 4 over 1 million, and here the metric will be 1 over 2, right? So now technically you can imagine that if there are only 2 items in the list out of all these million samples, you were still able to retrieve like 1 out of 2. So you did a pretty good job, right? And this is not that important, because out of 1 million you have a higher probability of choosing like any 4 items. So somehow like your metric should be able to capture this, right? And right now the problem is it is not able to capture this well, and that is why the recall is not a good metric, which won't work. Okay, so you can discuss like this recall with your interviewer, and that is a good way to go about this problem. Now let's look at another problem. Let's look at another metric which is known as precision. Okay, so what precision means is that what precision means, so mean average precision, so what precision means is that it, instead of dividing it by k, by all the item, it divides it by the number of items. Okay, so for example, in this case, let's say your model outputted two things. These are the, like, these two rankings. So here, like, out of 5 it outputted 2 dogs. So you can imagine that 2 out of 5 and 2 out of 5, in both cases it is giving you 2 dogs out of 5 spots. So that is the value. So while it improves upon the recall metric, what happens is that in this case, you can see that this is a better model because it is predicting a dog at a higher value, at a higher position, like at a higher rank. It is predicting a dog, and this is predicting the dog only at second position. Whereas, like, the model is measuring both of their precisions to be equal, which is not correct. So although it is like a better metric than recall, the precision is not a good metric. Now, the another thing which you can do is basically you can compute something called mean average precision. And what mean average precision actually means is that, for example, let's say you have like this sort of list. Okay, so then you can imagine that you are you so your number of predicted items are k. So you can measure precision at the rate 1, precision at the rate 2, precision at the rate 3, and precision at the rate 4, precision at the rate 5. So in this case, let's measure like precision at the rate 2. So here, out of 2 spots, the dog is only present in one place. So your precision at the rate 2 becomes 1 over 2. Similarly, precision at the rate 3 is still 1 over 3. And then precision at 4, here in the first 4 spots, like, you have 2 dogs. So it is like 2 over 4, which is 1 over 2. So your average precision here is 1 plus 1 over 2, 1 over 3 plus 1 over 2 divided by 3. Okay, so this is like the average precision, and that this actually takes into account like the total value. So this actually takes into account the it takes into account the position as well. And it seems to be like a good metric, because imagine for a moment that, let's say, you predicted all the 5 dogs in all the correct places. Okay, so 1, 2, 3, 4, 5. Then in this case, your metric is actually that you predicted like five of these values. So precision at the rate 1 is 1 over 1, and then it's 2 over 2, 3 over 3, 4 over 4, and 5 over 5. And when you add this all will cancel out to 1 plus 1, and so on till 5 times, divided by number of precision, which will come out to be 1. So your precision will be 1 if you manage to predict everything perfectly. And so you can use like this type of metric very well. And that's like a good choice in practice. There is another metric which is known as DCG, direct cumulative gain, and it is like a bit tricky. So what it does is, so what like DCG actually does is that, so let's say that you have like, so let's say your query image was a dog. Okay, so this is meant to be a dog. I'm sorry, I'm not able to draw a dog that well. So you have a dog, and in this case, let's say your model actually predicted the outputs in this sort of rank. Okay, so it predicted it in this sort of rank. So this is like the highest rank, and then it predicted second, third, fourth, fifth, and the numbers at the bottom are actually indicating what is the correct ground truth order of these images. Okay, so for example, if you see this dog, so this is like a ideal ranking. So if you see here, like, the dog is the highest rank, then which is a rank of 5, and then another dog which is a rank of 4. So you can imagine that this is like a ideal ranking. So to compute this metric, you need to know, like, for n images, like, what is the correct ranking, and then you need to know what is the actual ranking which is produced by the model. If you know that, then you can calculate this metric as follows. So you can actually, so what you can do is, you can, so this position is 1, right, because this is like the topmost rank, and the model gave it a position 5, right? So so model like gave it a highest rank. So you can actually divide like the ranking, which in this case is 5, by log of 1 plus the position it is at. So here it is at position 1. Similarly, here if you see, you can compute it as 4 over log of 1 plus the position it is actually at, right? So 1 plus, sorry, 1 upon log of 1 plus 4, which in this case is 1 over log of 5. So you can actually estimate like this gain for all the positions, and that is actually what is known as NDs. So you calculate like this gain the ground truth for the ground truth ranking. So let's say you have a query image, you predicted 10 stuff, and then in that 10 stuff everything is at the correct place. So what is the maximum gain you have? And similarly, like if you predict any ranking, what is the gain which you could have in that way? And let's say those you predicted the perfect thing, then your metric will be 1, otherwise your metric will be low. So in this case, like the idea is, if you calculate the gain on your ranking of your model, and if you calculate the gain on the ranking of on the ground truth ranking, then obviously you can get some value. And if this value is 1, then you built a perfect model. If this value is something between 0 to 1, then you built like a okayish model, and higher value here is better. So now the problem is that this assumption relies on one thing. It relies on, okay, that for a given query, what are all the possible rankings which you could get. So for a chair, what is the perfect ranking of the outputs? So let's say for a chair there are 1,000 options. So then what is the perfect ranking of all those 1,000 items? So that is something which you need to know beforehand in order to compute this type of gain. But in practice, nobody knows that, right? Nobody knows what are like the. So if you have 1,000 items in your inventory, you don't know which is the correct item. Okay, cool. So now let's look at the online. So coming at this, like what are like the best metrics which you could use? So either you could use NDCG, or you could use the mean average precision in your case. And mean average precision is also a metric which is used in object detection type of literature, and that's why like you can also use it in the ranking, and that is a really important connection which you can make. Okay, so now coming to the online metrics, let's say you deployed your model, you want to see how good it is. So what you can see is that, let's say your system got a input a dog, and you spitted out a bunch of dogs. So if your user clicks on your recommendations for a long time, like if there are a lot of users who clicked on your recommendation, that means your thing is doing really well. So you can actually capture this on the fly click-through rate for your recommendations, which is like the number of clicked images and the total images you suggested, and that will actually give you a good idea about what your recommendation, like how well is your recommendation system doing. Okay, so that is like a really thing. And another thing, like what you can do is that, okay, once a user opened a product, like how much you can calculate, like how much time did he spend on that web page, and what was like the time, how much time was spent on the web page of the products which you actually recommended. And if someone actually spent a lot of time, it means that they are actually very interested. Now one thing is, let's say for example, a person clicked on an image, and then he opened it, and then he went back, right? Like he went to cook or something. The page is open, and there is no way for the computer to know whether the person is actually reading it or not reading it. And that's like one of the problems in calculating that time. But you could solve it by actually tracking the face of a person through his webcam, or tracking like maybe his eye movement while he's looking at the screen or something like that. But technically I think it will still be a problem for Amazon. And if Amazon were to actually track your eye gaze, or maybe whether you are present in the frame or not, that will require like some on device processing, which is not really something I am pretty sure like a lot of customers are not interested in getting their things to be shared in this way by some company. They are obviously not so if you go to Amazon, you are obviously not comfortable if Amazon is monitoring you via your webcam, right? Because that's like a lot of personal information which you don't want to share. So I think this problem will still remain in the click-through rate. Okay, so now that you know what is good, what is like your data set, what is your model, what's your ML problem, what are the metrics which you could use, what is like how does the model look when you are trying to serve it in the real time? Okay, so let's talk a little bit about that. So there are two ways. Okay, so one thing is that, for example, you have an input image, and you want to know like how good it is, right? You want to compute something, you want to compute rankings in it. Okay, so let's say you have like a database of like million images in your inventory, and you so for all those images, like you have already trained, like so you have already trained a model, and for all of those images in your data set, you have already pre-computed those embeddings and stored them in the memory. Okay, so you have already stored them in the memory. So you have essentially built a database which is like item 1, so like image 1, and what is its embedding, image 2, and what is its embedding. And right now, when a user is uploading a image to Amazon to search for relevant things, so you receive a query image, and then you have a embedding generation service, and what it does is it first pre-processes the image, and then it passes this image through the pre-trained model and calculates its embedding. So now you have this embedding, and you have like a database of other embeddings which you have pre-computed, and you can rely on so you can rely on so you end up in this sort of representational space. And what you can do is you can imagine that, okay, your model is looking here, and then you are computing like this sort of representation. You're computing like the Euclidean distance or maybe cosine similarity among all the items here. So that's how it will work, right? So you can imagine that for the query image which you computed the embedding, you're calculating the cosine distance among all the million of images which are already stored in the memory. So if you look at this, actually the problem is you will start noticing several inconsistencies. One is that if you run a algorithm like k nearest neighbor, you typically have to store the entire inventory data in memory. So for example, if you have, let's say, 1 billion images in your inventory, then obviously you have 1 billion embeddings, and there is no way you can compute all these embeddings in the system RAM. So you will have to actually put all your database into some server, and then when you query it, it is gonna take like a lot of time to query it. And obviously you don't want to wait for 20 minutes for your page to send your query and then your items to return. So this is a big problem, that the size of your database grows linearly with the number of objects you are trying to store in it. And that is like a big problem in such kind of nearest neighbor algorithm. And another thing is, if you rely on measuring the distance of your query with each of the possible items in the database, if you have a lot of items, it is gonna take a lot of time. So that is not really good. So now the key point is that if the time is taking, if you are concerned with like matching everything and it's taking a lot of time, can you do better? Can you like somehow trade off like the accuracy with some quickness thing which you can do? And that is something which you can do, right? So there is something which is known as which is known as approximate nearest neighbor. So here what you do is that you try to build a tree for all the items in your data set. So for example, let's say I'm trying to search for an umbrella. Okay, so here you could have like all the possible tools, all the images which are belonging to a tool, and then there might be a tool which is, let's say, hammer, and there is a specific category related to umbrellas. And then the point is you will rely on umbrellas, and you can traverse this tree, and once you reach a particular node, you know what items are associated with that category, and you can actually bring those items into the memory and only compare against that. So in this case, the amount of time, so let's say you receive umbrella query, the amount of time it takes you to reach the umbrella node is at most the depth of the tree. And assuming that your tree is balanced, then you can actually run this operation in a logarithmic time. And then once you get all the images which are present, which are actually like umbrellas, you can actually run the nearest neighbor in only those regions. So let's say this is like a space of all the possible, so let's say these are all the possible items your inventory can have, and you're only searching for umbrellas, then maybe only this region is the one which is like a possible umbrella region. And what you can do is you can converge upon this region, and then you can only run nearest neighbor in this region. So you never run computation in these other regions, you only run your computation here. And since your region is very small, since your R4 is much smaller than the whole R, it will take very less time. Now another way is that what you can do is like you can map like all the umbrellas. So let's say if like you're searching for an umbrella, so you can like take an image and you can build a hash table. So let's say you have images of an umbrella. So let's say you have umbrella 1, umbrella 2, umbrella n. So for all of these images you have pixels, and somehow you compute like a hash function which recognizes that these all are umbrellas. So this hash function will give you a value, right? And this value is actually a key. So let's say for all the umbrellas, you can actually hash them to a constant value, which is, let's say, some embedding E. So then you can build a database which contains E along with all the embeddings of these other umbrellas in your embedding E1, E2, and so on till En. And one way, like, you can, so now then the problem reduces that, okay, you are given like a lot of these values and you want to build something which can map like all the umbrellas into just one value, one stable representation, which doesn't change if you have like umbrellas, maybe a red umbrella, a blue umbrella, or something. But if you can build that sort of high level representation, then you can do a pretty good job of like hashing them into these buckets. And when you like receive a query umbrella image, then you can actually hash it and compute its key, and then you can index into your database, and you can know, okay, this is the umbrella hash I computed, and you can know what all items are stored in the memory, in your stock, in your inventory, which you can recommend. So that is like a really good job. And obviously, if you want to learn a representation from images, like something which is like an umbrella, no matter like how many umbrellas you have, some representation which always stays constant, you will have to actually use a neural network. So in a neural network, what happens is that in the higher, so if it has several layers, the layers which are high, they generally encode like features which are of high level concepts. So generally these features don't change even if you change like the input umbrella which is sent. So if it's an umbrella used in the US or an umbrella used in India, or maybe an umbrella you created out of a craft, then the assumption is that the higher layer of this neural network will not change because it is a stable representation, and this has actually been shown in practice. So once you get like this type of representation, you can easily use it to compute that. Okay, so the key point is that we want to know like so when we are doing querying of such a system, what type of algorithm should we use. So if your inventory size is very small, you can use like you can use a exact nearest neighbor. And if your inventory size is like pretty big, then you can use something like a k you can use a approximate k nearest neighbor, and you can then get like the answers. Okay, so it depends on like what you want to know. And obviously, one important point here is that the interviewer may ask you to like implement the neural network which will try to do this sort of ranking, compute these type of embeddings. And you should be familiar with these systems like FIS and ScanNN, which were introduced by Google, and it would be pretty cool. And if you have like time remaining, there are some other things which you can talk about. So for example, if you have like if you have image metadata like tags, or like your image was captured in some region, then you can use that. Similarly, you can build hierarchical representations. So instead of like building like this tree structure here which I was talking about, based on tags, what you can do is you can actually build some sort of graphical representations which looks at the objects and clusters them. So then you build some sort of scene graph, and that will actually be good. And then you can use to get like more labels, what you can do is that you imagine that you have a network which you have trained, and then you're given like a unlabeled data, and your network is actually giving you the possible class it is, and then the human just has to verify whether the network's output is correct or not. So instead of the human trying to find like the 1,000 classes an object belongs to, we will just tell the human, hey, this is a network and it predicted that this image is of an umbrella. Is the network correct or not? So from a human's perspective, he just has to answer the question yes or no, and he doesn't have to worry about trying to look at all the 1,000 categories or all the possible categories and try to find whether it's an umbrella or not, because the second thing is like very tough. But giving a yes no response is generally very easier for humans to do. So once your neural network is like really good and it has been trained on a lot of data, it is having a very low error rate on some classes, you can use it to collect like more data. And if you have like certain classes which are like not, which your neural network has never seen before, or your neural network is doing very bad on, so for example, it is doing very bad on, let's say, cats. So then what you can do, obviously you can't use this neural network to predict something, then you can actually have the humans go and take photos of the cats and label it, then you can train your neural network again. So that is like the whole thing which you can use to talk about here. And so in summary, like this is like a nice representation of whatever points we discussed, which Alex Zhu has been kind to share in his book. And you can look at all of these. So in general, there are like five seven things which you need to do. You need to clarify the requirements, which is, in our case, we had that conversation between the interviewer and the candidate. You need to discuss like how it will be framed as an ML problem. In our case, we discussed that the problem of visual search is actually a mechanism to build a computer vision system which can rank the outputs, retrieve the images, and rank them according to their similarities. In data preparation, we discussed that, okay, we have like this a large amount of data. We can either get data by a user, by a human in loop, or via relying on fully supervised learning. In model development, we discussed, okay, we can rely on a CNN or a transformer, and then we can train that by using like some sort of contrastive learning. And for evaluation, we discussed like two kind of metrics, which is offline metrics and online metrics. And we discussed like what are the trade-offs of each of them, and then when you're actually serving your model, what can happen. And then we talked about like the trade-off between, if you have like a large number of inventory items, then it will take a lot of time to search, and if you have only some, it will take only some time. And then there are some other talking points which we discussed. So the key point is that these are like 7 steps. So 1, 2, 3, 4, 5, 6, 7, and one. If you are approaching any system design interview, you have to actually structure all your problems around these 7 points. And the rest of the problem just boils down to whether you have the knowledge of how to translate a given system. So this point is the most difficult one, that if you're given a problem, how do you actually make a ML task out of it. But hopefully, as we cover the rest of this book, it will get better. So thanks for watching, and I hope you had a good time. And the next video I am going to cover is so these are like some references, and you can read more about the Curse of Dimensionality and the Scan library by Google, which does this sort of ranking for a given amount of images, and that should be a really good idea. Now the next time I am going to cover something called the Google Street View blurring system, and that is like going to be a pretty cool video. But that's it for now, and thanks for watching. And if you really liked my video, do subscribe it, and I hope you had a good time. Please move on to the next video if you are interested. Thank you.